All right, let's go ahead and continue doing more application problems. Let's skip number 3. It's basically the same as number 2. We can come back to that at a later time if anyone wants me to. Let's look at another kind of problem here. In this problem, I've been told that the population of a town grows at a rate proportional to the current population at time t. The initial population of 500 increases by 15% in 10 years. What will the population be in 30 years? Well, so let's go ahead and we'll let P of t be the population of town. Then this problem tells me that the rate of change of the population, the rate of growth, d capital P dt, is proportional to the current population of the town. And that makes some amount of sense if you have a lot of people. Presumably you are having a lot of babies, and so the rate of change of the population is sort of high. And if there's only a few people, well, they can't have babies that fast, and so the population can't be changing that quickly. Okay, so we know dp dt equals k times p. We know that p at time 0 is 500, and we know that p at time 10 is 15% bigger than that. So what is that? That is 575, right? So we can use that information. That's p at time 10, not p at time 0. We can use that information and hopefully we can get a solution to the ODE. So again, here we have a constant of proportionality that it's not explicitly given. Okay, so hopefully by now we can just look at this ODE and we know capital P of t is AE to the KT. And now our job is to find A and K. Again, if you wanted to, you could use Maple, but at some point you just have to know the solution to dp dt equals K times P. It's AE to the KT. Now this guy, after a while you just know this is the initial condition right here. Again, you could go through, set 500 equal to P of 0, blah, 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 but you'll get this. P of t is 500 e to the kt. You could use Maple if you wanted to from here. Let's go ahead and, sure, we'll try that out. We want to solve 575. If we plug, we want that to be 500 times e to some constant times 10. We wanted to plug in time 10. We want to solve that for k. And I don't really like that answer. That's sort of ugly. I could use that answer and simplify things and get a nice exact answer, but it's probably easier just to get a decimal approximation here. So 0.014 we'll say. So we can say P of 10 equals 575. Maple. That tells us that K is equal to 0.014. And so P of t equals 500 times e to the 0.014t. And then if we wanted to, we could plug in time 30 and be done. All right. Number 4 and 5 are very similar. One was a population growth model. This one is this is an exponential decay model. The radioactive isotope of lead, Pb209, it decays at a rate proportional to the amount present at time t, and it has a half-life of 3.3 hours. If 1 gram of the isotope is present initially, how long will it take for 90% of the lead to decay? So this is very similar. We'll let A of T be number of grams present. All right. We know that, again, it's decaying at a rate proportional to the amount present, so dA dt is a constant times A. So again, we have A of T is however much there was initially, A naught times E to the KT. I'm using an A naught here because I think that using a little a and a big A is sort of weird, so I used an A naught. All right, we know that 1 gram is present initially, so our A naught is 1. So A of T is E to the KT. We want to know how long it'll take for 90% of the lead to decay. Now we need one more piece of information before we can do that. We need to figure out what the K is, but we're told that the half-life of Pb209 is 3.3 hours. So we can say that after 3.3 hours, you're left with half of however much you started with. So in this case, I know that I had 1 gram that I started with. So I know that 0.5 is equal to A of 3.3, because after 3.3 hours I have half as much as I started with, so that's E to the K times 3.3. So now if I wanted to, I can say maple. I want to solve 0.5 is equal to E to the K times 3.3. So the constant is negative 2.1. Negative 0.21, I think. Yeah. Okay, so that tells me A of T is E to the negative 0.21 T. And then that's it. So now if you wanted to find out how long it'll take for 90% of the lead to decay, you just have to set A of T equal 2.1 and solve for T. All right, let's do one more for today and then call it good. This is a different kind of model. This is pretty much a logistic model. A student returning to campus from break has a flu and infects other students. Suppose that the rate of change in the number of infected students is proportional to not only how many students have the flu, but also how many do not have the flu. So let's talk about that for a minute. Why does that make sense? Well, the important thing here is that if everyone has the flu, no more people can be getting infected, right? So if that's saying if there's no one who doesn't have the flu, then you can't be infecting anyone more. Everyone already has it. So then the rate of change of the number of people who have it has to be 0, right? So whenever everyone has the flu, then dp/dt, if that's what we're calling the rate of change, dp/dt has to be 0 in that case. So let's go ahead and write this down. We'll let P of t be the infected population. We'll say d capital P dt. It's proportional to, so it's a constant of proportionality times the number of people who have the flu, which is P, times the number of people who don't have the flu. So that's how many people there are minus P, and there are 1,000 people. Okay? So this is a logistic model. And the good thing about this is if P of t is 0, then we have a rate of change 0, which is good. If no one has the flu, then we just stay with no one having the flu. That's nice. And if P is 1,000, then dP dt is 0 also. So if everyone has the flu, then everyone has it, and we can't infect anyone more. So this is the model we'll use. We can go ahead, let's see, we know that P at time 0, there's just one person. Notice that this is a nonlinear equation. To solve it, you'd need to use separation of variables. And to do the integration, you'd need to use partial fractions. All of which is very doable, and I suggest that you practice doing that because I do love these kinds of problems. Now, for the homework, however, you are certainly welcome to just use dsolve. So let's do dsolve p prime of t equals a constant times p of t times 1,000 minus p of t. I would like p of 0 to, without knowing the constant of proportionality, I won't be able to solve for k, and so I won't be able to solve the initial value problem. So here's our solution. We know that p is 1,000 over 1 plus 1,000 e to the minus 1,000 kt times a constant, so that's fine. From Maple, we know that p of t 1,000 over 1 plus 1,000 a e to the minus 1,000 t. I think that's what Maple said. Minus 1,000 kt, that's right. Okay. All right. And that's all we can say. It looks like this problem is poorly phrased. I didn't give you enough information to do the rest, so you'd have to just so this is the model. If we had another condition like p at time 5 equals 10, actually let's just do that. So let's assume p of 5, there are 10 people infected after 5 time units, whatever the time units are going to be. So then we could go ahead and set p to be this expression, 1,000 over 1 we could go ahead and solve for substitute in t equals 5 into p. We would like that to be equal to 10. And we'd like to substitute in t equals 0 into p. We like to get out 1. So we're reflecting the two conditions that at time 0 we have 1 person infected. At time 5 we have 10 people infected. Let's go ahead and solve that system of equations. I can solve this numerically. I could also just put a 10.0 here. There we go. So our A is, well, that should really be 1. And our K is 0.0005. So Maple, P of t is 1,000 over 1 plus, what was my A again? 0.999 e to the Now I'll combine those together. That's negative 1,000 times, well, let's just see, that'll turn out to be 0.4 t right there. And then that's it. Now you're done. Okay, so that's an introduction to some application problems. We'll do more of these tomorrow. You should be reading section 2.7 and 2.8 of the book.